Hello, everyone. Welcome and good morning. Uh, this is data structure, chapter 1, first chapter and part 2. So today we will start with data abstraction sections. Okay, so we will introduce many kind of new data structure, and also uh, in especially I said before that we will learn 6 type of data structures in this class. Then how we can define that new data structures? Okay, so we need some format to define new data structures. That format is data abstraction in here. Okay, so data abstraction uh, looks like object-oriented design method. Okay, so here we have to define object to store the data. Okay, and also there should be operations to deal with this object. Okay, so we need design. This is a kind of a design phase. So before we implement this design, we must finish or we must complete this design. So with object and operations. Okay, so if some design consists with object on operation is called object-oriented design. Okay, this is also can be considered as object-oriented design. Okay, so here in this class we will adopt object-oriented type design to define new data structures. Okay, so that design is called design abstractions. Design abstractions. Okay, so abstraction means that it is not concrete. Okay, that means that it is not so specific to implement. It just define the definitions. That is data abstraction. Abstraction means that is not so concrete to implement. Okay, so so if we consider previous polynomial example, then we will we must have object, okay, to store polynomial data, and also we need some operations to the polynomials. Yes, so polynomial is new data structures. In order to define new polynomial data structure, we will use object and its supporting operations. Okay, we just specify this object and the operations. Then it is independent of how it is implemented. Okay, so if we implement this polynomial using array or linked list. Okay, so it's the next step. Next step is implementation. So if we think data structure itself is design phase. Okay, so this is a data abstractions. Because we will use this data abstraction method in the later chapters, we must introduce what is a data abstractions. So I think that data abstraction means that it is object-oriented design. So in short, it is called ADT, abstract design type, means that it is object and consists of object and operations. Okay, so it is independent of implementation of the operations. So implementation is next step of this design phase. Okay, so that means that it is not uh, uh, programming code. It is called pseudocode. Pseudo, Pseudo. Pseudocode means that it is not real programming code, but we will adopt this pseudocode to define this abstract data type. Okay, so there is no strict syntax to this pseudocode, but we will follow some syntax from the C language. Okay, so let's go on. So this is a example of natural number data structures. So if we consider new data structure, this is a new data structure. And then how we will define these new data structures. We just adopt ADT, abstract data type, natural number here, and this definition consists of two parts, object and functions. Yes, functions is operations. It's just the same meaning in here as operations. Okay, so we will define object to store data. Okay, so that means that in order to store natural number, we need some ordered sub-range of integer, starting at 0 and ending the maximum number of integer in the computer. Okay, that is object definition. So it's the definition of a natural number. Natural number means that positive integer number including 0. Okay, so that is a natural number definition. So this object definitions describe that. And also functions. Functions, what kind of operations we can apply to the natural number. So that is addition, add here. Okay, so natural number, add, and the parameter of this operation is x and y, two parameters. And if, yes, this is a definition of this operations. Okay, this is addition operation included in the computer language. Okay, this add, English definition add functions is operation of this natural number data structures. Okay, so and anything else, any other operations can be defined following these add operations. Okay, so here is complete abstract data type of natural number. Okay, so there are add here, and also subtract can be defined. Subtract minus can be defined. Okay, so if it is a negative number, it returns 0, else it will return x minus y. And addition, we can consider again x plus y is less than integer max number, then return x plus y. Otherwise, it will return int max. Yes, the maximum allowable maximum number in the computers. Okay, so it is this one can be said that it is defined as, okay, so colon and equal means that it is defined as meanings. Okay, this is abstract data type syntax. Okay, so we will use abstract data type later chapters. Okay, next topic in chapter 1 is performance analysis. Okay, so it's a little bit complicated, but and hard to understand, but it is basic to start with algorithms. Okay, so performance analysis means that how much it is good. Okay, so we need some criteria to check how much it is good. Okay, so in here we are always interested in time and the space requirement of the algorithms. Okay, so performance analysis is related with algorithms, how much this algorithm is good. Okay, that is the meaning, concept of a performance analysis. So we will decide based on time and space. Okay, so space complexity means that how much amount of memory will be necessary in the algorithms. And the time complexity, okay, means that how much time, computer time, it needs to run the algorithms. Okay, so time means that computer time, and the space means the memory size. Okay, so that is the two typical criteria to decide which algorithm is better algorithms. So in here we will detail on the criteria. Okay, so performance analysis means that space complexity analysis and the time complexity analysis. Okay, so space complexity means that the memory or storage requirement, and the time complexity means that computing time. Okay, so this performance analysis means that it is a machine independent. Okay, so machine independent means that it is not different, not depending on the computers. That is a machine independent. But in contrast, performance measurement means that we will check the number of the performance. That means that it depends on the machine. This machine means that the computer, yes, computer, how much the computer is fast. That will affect the measurement. Okay, so that is a performance measurement. So both methods are used in the performance measurement of algorithms, but which one is more uh, objective or more fair? So I think that this machine independent method is better measurement to decide which algorithm is good, and especially among these two performance analysis method, space or time? Which one is more important to you? So in the 1990 or 1980, this space complexity is much more important than time, because everyone can wait. And also memory was very expensive at that time. But how about nowadays? Nowadays, nobody can wait. Okay, and memory price is very low nowadays, so we can increase memory as much as possible. But no customer will wait. Okay, so nowadays time is much more important than space. Okay, so we will concentrate on this time complexity. Okay, so next is time complexity. We will skip space complexity. Yes, space complexity is in the text our class, but we will skip that one, and we will check only time complexity. Okay, so this time complexity analysis method, we will interested in the number of steps in the program. Okay, so this step, what is a step? Program step is a syntactically or semantically meaningful program segment whose execution time is independent of the instance characteristics. Okay, so that means that one program step is one line in the program. Okay, so that is line counting. How many lines are there in the program? That is a time complexity analysis. Okay, so here is example of step counting to analyze time complexities. Okay, so left part is program. This is a program. I want to analyze time complexity of this program, or it is called algorithm. Okay, so algorithm and program are the same meanings in here. So here, this program is implemented using recursive functions, and then we can count the number of execution, number of lines in the program. So here, right is the calculation of step counting. We will check what is SE. SE is steps per executions. So one one line or one statement or command can be calculated. Okay, so R sum is no steps in the execution. It is just a function name, and this brace has no steps. And the if line, yes, this is a one line we will execute in this program. So if is 1, and how many this line will be called in this recursive functions. Okay, so the data is n. Data is n. Then this line will be called n plus 1 times. Okay, and also the inside of this if statement has only one line. Return are sum and the parameter plus list value. So here this line will be executed one step. And how many these lines will be called in these recursive functions? This line will be called n times. And so the total steps are n because 1 times n equals n. And the next line, return 0, will be executed one step, and it is executed only one time in the whole program. So that is n. And this brace has no steps per execution, and 0, 0, and equals 0. So in this program, we can sum all of these steps, total steps. That becomes 2n plus 2. Okay, so that is total step counting of this program. Okay, so this is how we can count steps in the programs. That is time complexity analysis. Okay, so you just count the number of steps. If we assume that there is data n datas. Okay, so in this example, this n means that data size. Okay, so here is important, and let's go on. So the time complexity means that this for some fixed n, so data size, the time, the real time taken will be different depending on the instance. Okay, so sometimes it will be executed very fast. Sometimes it will be executed very, very slow. Okay, so this example shows that how much the time will be different. Okay, and this example is a such example. So the data is 3578. If such number is 5, then we will search faster than searching 7. Such number is 7. Because if we consider sequential method, 5 will be found 2 times, 2 steps, and the 7 will be found 3 steps. Okay, so that means that 5 will need less steps than 7. Okay, so that means that time complexity analysis, the uh, the the necessary steps will depend on the different instance. Okay, so we can consider some algorithms case as three case: worst case, average case, and the best case. Okay, in time complexity, which one will be used? Which one will be useful? Okay, so every humans must be very optimistic rather than pessimistic. But in time complexity analysis, I think worst case is most important. So in the program development, we must consider the worst case. Okay, in worst case, how much time will be taken? Okay, so that is important. Then best case. So best case is rarely seen because it is not so useful in program development. And sometimes average case is also important, but worst case is much more important. So we will consider only worst case, most commonly used. So that means that it is a concept of guarantee. So we can say that we can guarantee the time of this program using worst case. Okay, so uh, and also we must consider, we must introduce new definitions called asymptotic notations. Asymptotic notations. So asymptotic means that the number of data goes infinite. Okay, so in high school mathematics, we already learned that the limit. Okay, so n goes to infinite. What happens to the algorithm or to the programs? That is called asymptotic notations. Okay, so if we consider the previous one, worst case, average case, and the best case, so I think that the exact step counting is not so necessary because the concept of a step is not even inexact itself. Okay, so step, we defined that it is a line in the program, but that concept is not so exact. So, and also, furthermore, we must consider the worst case. Worst case means that n becomes a very, very large one. Data becomes very large one, big data. Then the exact time, step counting is not so important. Okay, so for example, 2n square and n square. Okay, if you consider these two values, of course, 2n square is larger than n square. Okay, but how about n becomes very large? Then I think this 2n square and n square becomes very similar. Okay, when n goes to infinite, very large size. But how about the 2n square and 1000n? Can you think which one is larger one? It depends on the number of n. If n is about uh, 10, 10, okay? 10 square means 100, 200, okay, on the left. And on the right is 10. It is 10,000. Yes, it's much more this one. Right is larger than left. But how about n becomes large values, especially more than 10,000? Then I think left becomes much more larger than right. Okay, so we can see that n square is much larger than 1000n if data size n becomes very large enough. Okay, so we can think that if data size is not so big, I think the time complexity is not so important. So time is much more important than at the data size is very large. Okay, so that is asymptotic notations. Asymptotic notations. So especially when data size n goes infinite, what is the time complexity? Okay, so in order to analyze asymptotic notation, we introduce new concept, new new symbols. Okay, before that, this shows that if a time complexity is 1, it means constant, and the log n means logarithmetic, and n means linear, and the n log n log linear, log linear uh, is n log n, and n square is uh, quadratic, and n cubic means cubic. Okay, so this kind of time complexity, okay, and there is also two exponent n means that's exponential, and n factorial also can exist. But how about this real instance of a data size, number of data? Yes. So if a number of data is small, 8, then there are not so big difference depending on this time complexity. But if data size become large, 32 is not so large, but if we only consider 32 data size, then exponential has very long time, and the factorial is much more long time. Okay, so if n data size goes to infinite, very large size, then I think this cannot be used. Okay, only I think square can be used algorithms. Okay, if we plot the tables data in the graph, here is one. Okay, so this is a n data size, and this is a time. Okay, so if log n does not increase time rapidly, but n log n and n square and the 2 exponent n goes very, very steep increase in the graph. Okay, so that means that we only consider this time complexity in the useful algorithms. Okay, so if n goes 1 million, okay, and uh, log 2n and n square n cubic, if it goes to n fourth exponent 4 and 2 exponent n, it is non-useful. It is not useful algorithms. It takes very, very long time, so we cannot use that algorithms. So we need some asymptotic representation of time complexity for each algorithms. We need new symbols to represent asymptotic notations. So in here, the previous example, 2n square can be equivalent to n square. So we will classify some time complexity as class. Okay, when we finish our time complexity, there may be a very specific formula to count the program step, but we consider asymptotic notation. That means that when data goes very, very large enough, then it does not it has no meanings to analyze a specific uh, time complexity. The only important thing is what is the class that algorithm belong to. So here 2n square plus 100n, as I said before, n square is much more important than n. Okay, so this term is not so important. Only this term is important. So this term is called dominating term in the time complexity. So we can say that this total time complexity belong to n square. Okay, so we only consider what is the class, time complexity class in the time complexity analysis. Okay, so we can say that asymptotic notation O, this is O, but it is a big O, capital O, means that fn, function n, equals big O gn if there is positive constant c and constant n0 such that this one. Okay, so the coefficient c is not so important in the asymptotic notations. So that means that 3n plus 2 can be represented as big O n because this constant is not dominating. Dominating is here, and 3 coefficient is not so important according to these definitions. So 3n plus 2 belong to class n. This is a class. So we represent this 3n plus 2 as big O n. The same way 3n plus 3 also can be represented as big O n. Even 100n also belong to big O n. But if there is another dominating terms, n square, quadratic, this is non-dominating terms. Okay, so we consider only this dominating term. Okay, 10n square belong to big O n square. And how about this one? This one is exponent. N square is not dominating in this case, and this is a dominating term. Okay, so we can say that big O 2n square 2 exponent n. Okay, so that is asymptotic notations. So what kind of class in the asymptotic notations? Yes, this is a whole class, whole types of time complexity 1, 2, 3, 4, 5, 6, 7. Yes, we only use 7 type of asymptotic notation class. Okay, here I think this 4 class is useful algorithms. Otherwise, it is not so useful algorithm. So we just discard that algorithm even if it is developed. Okay, so n square, it takes long time, and 2 exponent n is extraordinary large number of steps when data becomes very large enough. Okay, so it is not useful. So useful algorithm must belong to this log n big O n, and big O n log n, and big O n square. Okay, for useful types. Okay, so that's about how we can represent asymptotic notation. Yes, it is if it is a constant, we can represent big O 1. And n square is not big O n because n square belong to another class rather than n. Okay, and it is the same. And 2n square plus 100n, dominating is n square, so we just represent big O n square. Okay, yes. So dominant term means that if there is an n square term and an n term, then n square term is dominant term. We just throw out or discard minor term, yes, or constant also. So the name of this one, logarithmetic, linear, log-linear, and quadratic, and cubic, and exponent. But only these 4 types are useful, useful class in asymptotic notations. So you must remember this one. Okay. So now we explained time complexity or performance measures until now. So why we need this performance measures? So in the later on, we will consider algorithm 1 and algorithm 2. Okay, so there is alternative two algorithms for one goals. Then which algorithm is better algorithm? Which algorithm we will choose? Then we need some criteria for these decisions. That criteria is time complexities. Okay, uh, so uh, so in there, if one algorithm one goes to n square, and algorithm 2 n square here, and algorithm 2 goes to n log n. Okay, then which one, which algorithm is better algorithms in the view of time complexity? Okay, so in the previous slide, n log n is much more better. Okay, so we will choose these algorithms in these goals. So here n square algorithm is sequential search here. And n log n is binary search, belong to this n log n class. So if I want to search some data, then we will choose binary search rather than just a sequential search. Okay? Of course, binary search will generate result faster than sequential search. When data is very, very large, then the difference will be much more. Okay, so binary search will suggest the result very, very fast, but if you use sequential search, it takes very long time. No customer will wait. Okay, so we just choose algorithm 2 in this case. Okay, so in the later chapter, chapter 2, chapter 3, 4, 5, 6, later chapter, we always uh, learn new data structure and corresponding algorithms. Then which algorithm or which data structure is better algorithms. Better algorithms. Better algorithms. Then always we just analyze time complexity of uh, some algorithms, and then we just choose based on the time complexity, especially time complexity means that asymptotic notation, big O notations. Okay, so that's our goal to learn what is time complexity here. Okay, so that's very fundamental in data structure studies. So that is in the chapter 1. Okay, so that's the end of chapter 1. Okay, so we just introduce what is a program cycle. in the last time. So there are 5 program cycle steps. Among them, data structure belong to design phase. Okay, so today in design phase, if we define new data structure, we will adopt abstract data type, and also we need uh, some criteria to decide which algorithm is better algorithm. So here we use time complexity. So time complexity can be represented as big O notation, asymptotic notation. Okay, so big O class has only 7 class. Among them, only 4 useful uh, asymptotic class. So you can analyze every algorithm using asymptotic notations, and then you can decide which algorithm is a better algorithms. Okay, that's all today, and that's all for the chapter 1. Okay, thank you.